3, 5. So for this one, the difference is this truss structure has an external load like this one, and it has a kind of support settlement, right? You have seen this, but we do another practice to see how we cope with support settlement. We have 3 nodes, node 1, 2, and 3, and 2 elements, obviously. All right. So we have 3 nodes. 3 times 2 means 6 degrees of freedoms, not considering the supports. We have 3 nodes. The number of nodes will be multiplied by 2, will be the number of degrees of freedoms. So we have 6 degrees of freedoms. I anticipate the total stiffness matrix should be 6 by 6. All right. I know the individual stiffness matrix for each element is 2 by 2 in local coordination system and 4 by 4 in global coordination system. So I start by assembling the individual stiffness matrix for element 1, 2, like this is for element 1. So this is E, this is I, this is L. Sorry, this is E, this is A. This is L, EA over L, right? And where does it come from, this matrix? It's coming from this one. You should always have this beside you. Should always have this beside you, and you know, C and S definition. It's xj minus xi over L, and S is yj minus yi over L. Okay, and we have AE over L. So this 4 by 4 matrix can be used and repeated for every individual element. All right. So I get back there. So that's why you see here cosine theta and sine theta. This is just the theta, but I strongly recommend to do CNS, like C is when we're talking about element 1 connects node 1 to node 2. You should write it down. It's connecting node 1 to node 2. So C and S will be x2 minus x1 over L, y2 minus y1 over L. What is x2? Where is x actually? X is here, y is here. So this is x, this is y. All right. So x for node 2 is 3 because x is vertical. It depends on you how you deal with your x and y. The coordination system. Welcome to finite elements. I'm very happy you made it today, but I'm very sorry you cannot register your attendance, because today those people who came late are able to benefit from pure knowledge of finite element without registering your attendance, because you're late and you should learn what does it mean to be on time. When we start at 9 o'clock, it means 9 o'clock. It doesn't mean 9:15. All right. So if you want to register your attendance, you can be on time next time. And it doesn't mean that I do register at the beginning of the class. Maybe I randomly do register at the end of the class at some point. If you want to learn something, you should be on time, not when I'm talking about some examples, a group of people come finding seeds and making fuss. So this is the lesson for today. So this is x, this is y. What is x2? 3 meter minus x1, 0, divided by L. This is 3, 4, that's 5, isn't it? If this is 3, if this is 4, it's 5 meter, isn't it? It's a triangle. This is 4, this is 3, this is 5. So this is 0.6. What is y2? 4 minus y1, 0, because this is y. The horizontal axis is y, divided by L, which is 5, which means 0.8. This is this one, and this is this one. This is C, this is S. And you don't need to deal with theta. It's okay if you want to deal with theta, which is the angle from somewhere to your element, but that makes confusion in some cases, and I don't recommend to use theta. I strongly recommend to use the definition of C and S, because it's very easy. It just needs you to read the X and Y for some points. Number one, which points? The points connects for that element. We're talking about element number 1, which connects node number 1 to node number 2. So I'm talking from I to J. I is the first, J is the second. All right? This is I, this is J. I is the beginning of the element, J is the end of the element. All right? So shall we do it for element number 2? Just for element number 2, it connects node number 1 to node number 3. You can say it connects node number 3 to node number 1. That's fine. But whatever you define, follow that for the rest of your calculation. Okay? For element number 2, it connects number 1 to number 3. So C will be xj minus xi divided by L. S is yj minus yi divided by L. And I is number 1, j is number 3. It means that x3 minus x1 divided by L. L is the L of element, the length of the element. Y3 minus y1 divided by L. All right? So it means that y3, what is y3? It means that y is a ruler. Every coordination system is like a ruler, which has a 0, 1 centimeter, 2 centimeter, 10 centimeter, 20 centimeter. The 0 is here. Put a ruler here. This is your ruler. Okay? This is your y-axis. Put a ruler. 0 is here. 1, 2, 3, 4 meter. This is 4 meter on your ruler, which you put in the y-axis, which is horizontal axis, and the 0, you put the 0 of your ruler at point number 1, right? That's a ruler. Put it there. Okay, this is 4 meter. Y3 is 4 meter. It's Y3. 4 meter. What is X3? X3 is 0, because X is another ruler like this. This is the 0 of your ruler. This is 1 meter, 2 meter, 3 meter. Okay? This is 1, 2, 3 meter. Okay? So X3 is 0, X1 is 0 again. divided by L is 0. For what? For S, Y3, 4. 3 is here. Node number 3 is here. It's 4 meters from 0 in the y-axis, right? Minus Y1. What's Y1? 0 divided by L for element number 2. What is the length for element number 2? 4. This is 1. 0 and 1. This is C. This is S. When you have your C and S, you can just assemble your 4x4 matrix for individual elements, right? This is for element number 2. This is for element number 1. So just you need to repeat everything for whatever number of elements you have. I just did the same thing for element number 2 as I did for element number 1, right? So you repeat this process for all the elements you have in your structure. All right? So we have 2 elements. Okay, we have 2 matrices 4x4 each. Now we need to assemble the big matrix for the whole structure, which I know in advance should be 6x6 because I have 3 nodes multiplied by 2, which means we have 6 degrees of freedoms. Degrees of freedoms means every node can move to the X or Y direction, potentially, if we do not consider the supports. Without supports, we have 3 nodes. Each node can move to 2 independent directions, X and Y. And that means we have 6 degrees of freedoms. Okay, we later on put some supports, that's another story. But before talking about supports, we have 3 nodes and 6 degrees of freedoms. So here we need to have a sort of 6x6. You can put it 6x6 empty matrix and just write, we have number 1, 2, 3, all right? And we have, see, we have this as a hint here and this as a hint here. It means that, for example, for this one, this is the first node, number 1. This is the second node, number 2, because it's connecting number 1 to number 2. This is connecting number 1 to number 3. That's why it's number 1, number 3, right? But for the total 6x6 matrix, you just start from 1, 2, 3, 4, whatever you have. Like D1x, I cannot write there. D1x, D1y, D2x, D2y, D3x, D3y. Just in an ascending format. 1, 2, 3. XY, XY. All right? Then it's suppose that it's empty. A 6x6 matrix full of nothing. And you need to bring all of these numbers into the right places. Right? You have generally you can have, because it's 4x4, means 16 elements here and 16 elements here. 32 numbers altogether. But you should repeat and bring every single number of those 32 to the right place into the big matrix, right? So, for example, which one? This one, minus 1.25. Where does it go? It goes to, because it's B1x, B1y. It goes to the column B3y and row D1y. The column D3y, which is this one, and D1y means the row number 4. No, the row number This is column D, 3y, and row D, 1y. Number 2, D1y is row number 2. Row number 2, column number 6. This is this number, right? So you should repeat this for all the elements there, bring them here. Just a hint, you always have some numbers at the back of your matrices. Here you're lucky and the number is 25,200. Okay, so it means that you should not worry about it. 25,200 comes here for all of the numbers, right? But if it was different between these two, what would I do? It's just a simple algebraic trick. For example, suppose that I had instead of the instead of this number, suppose that I had 50,400. Not this one. I'm just saying. Okay, I have 50,400. What I do is I say, okay, you can, instead of this number, I can say 50,100 for 50,400 multiplied by 25,200 divided by 25,200. Is it allowable? I'm multiplying by 1, right? I'm allowed to do so. I keep this one at the back of my matrix and I bring this one into the matrix, whatever it is. By this trick, I will have the same number for both matrices and it will continue the same. Which is in this case, this is 2, which means that multiply everything inside the matrix by 2. All right? You can just make up your matrices in a way that to have a same identical number at the start. So when you put everything together for the big matrix, you only bring one number to the back of your matrix, right? Does it make sense? So otherwise, the other way is just multiply these numbers inside to have nothing at the back of your matrix, which is annoying because it's a big number usually, and if it goes into the matrix, you will have to deal with a lot of zeros, numbers, 1,000, million. It doesn't feel okay to do so. It's good to have a big number out of the matrix and some numbers like this inside the matrix. Anyway, when we assemble the total matrix for the whole structure, we know that this matrix connects or correlates the deformations. This is the vector of deformations to the vector of forces. And for the vector of deformations, if you take a look at the structure, you can see 5 of the degrees of freedoms are restrained. And only 1 is can move, is open to move. So as you see, the only degree of freedom which is fine to move is for node number 1 in y direction, which means delta 1 y is free to move, right? So delta 1 y is unknown, free to move, we don't know what it is. Because of the support, the others are 0. 5 displacements are 0, aren't they? Because 2 are here, 2 are here, and One is here, delta 1x. X is vertical. Take a look at it, right? So 5 of the deltas are 0, and only 1 is non-zero, which is unknown. We should calculate it. So we only have delta 1y. And as you know that, usually when you have delta equal to 0, the corresponding forces here are support reactions, right? And when you have delta 1y as unknown, the corresponding force here should be a sort of external force, because when you have unknown deformation, it means that the node is free to move. And if it's free to move, you can have some external forces, right? Which is in this case is 1,000 kilonewton in the y direction, which means positive, right? So it's 1,000 kilonewton. If I hadn't had the support settlement, I would proceed with this process. I had 1,000 as the external force, and it means that you eliminate all of these 5 rows and columns. Number 1, 3, 4, 5, 6. Only the second line stays, and it says 1,000 equal to, or I write it here, 1,000 kilonewton is equal to 25,200 multiplied by 1.89 delta 1y. And delta 1y can be calculated easily, right? And you know what's the next steps. It's exactly like the previous case. However, we have a new guest here, which is the support settlement, right? We need to see how we can implement that support settlement into the process. If we didn't have the support settlement, this was the straightforward solution. We just go and eliminate rows and columns number 1, 2, 3, 4, not 2, 3, 4, 5, 6, and only number 1 stays there, and you can calculate delta 1 y very easy. Any question here? But we have a guest here like the support settlement equal to 50 millimeter to down against x-axis, right? We want to see how does it work. So this 50 millimeter is along with delta 1x, isn't it? If you didn't have support settlement, delta 1x was 0. But because of some problem in soil, whatever it is, in the beneath of your foundation, the whole support is going down. The foundation and your element and the soil is going down for 50 millimeter. There is still a support, but the support itself is getting down. It's having a sort of settlement for washing out the soil for any other reason. All right. So it means that this delta 1x is 50 millimeter, not 0. This is unknown. The rest are 0. These are really supports without any settlements, right? Still, we have this like 10,000 or 1,000, 1,000 kilonewton, and we know that the rest of them are support reactions. We don't know them, do we? So You remember that when I say, in the previous case, when I say we eliminate rows and columns number 1, 3, 4, 5, 6, or whatever it is, it really means that I am transferring this kind of matrix formation to the old-fashioned group of equations and getting some of them out, and some of others will be again transformed to the matrix form, right? I want to do the same here, but you can do it for all the 6 equations, or you can start with the second equation only to see what happens. What is the second equation? The second equation is f1y equal to this line multiplied by this column, isn't it? What does it mean? This number is 0.48 for now, the first number, which means that 0.48 delta 1x, I will write everything with all the things I know they are 0, plus 1.89 delta 1y minus 0.48 delta 2x plus 0, sorry, plus 0.64, not plus, minus 0.64 delta 2y plus 0 delta 3x plus or minus 1.25 delta 3y. I wrote everything. I know some of them are 0, but this is the second line of equations, right? I know delta 3y is 0, this is 0, this is 0, this is 0. The term, third term, fourth, fifth, and sixth term are 0, and I only have this part of my equation, the first term and the second term. The second term, delta 1y, is unknown, and the first term is 50 millimeter, that settlement. Just multiply 50 millimeter by this 0.48. However, everything has 25,200. All right. And if you say this is 50 millimeter and multiply it by 0.48 and bring whatever it is to the left hand side, it will be added to this 1000 kilonewton, whatever it is. The settlement works as an equivalent external force, right? Because 1000 kilonewton was an external force, sort of. So we have something else in the right-hand side, which is 50 millimeters times something. That comes to the left-hand side and will be added with whatever it is, if it's minus, positive, whatever it is, with the sign, by the existing 1000 kilonewton there. So it means that it's like the settlement mathematically is look like we have 1000 kilonewton as an external force and something from the settlement acting as an external force, because they are combining together in the left hand side of the equation, right? Is it clear? So this is what we do here. This is what I said, and you need to calculate delta 1y, and Can you calculate, I know this is 1,000 kilonewton. Can you calculate this part and compare it to 1,000? What is this part? 25,200 multiplied by 0.48 multiplied by 50 millimeter. But you need to transfer the 50 millimeter to meter, right? I want to see, compare them. I want to compare this to 1,000. How does it work? Please calculate. Louder, please. No, it cannot be. It should be comparable to 1,000. It's this one. Actually, it's not this one. Sorry. This is, okay. You need to calculate this one. What is it? What? Yeah. What I did is 25,200 multiplied by 0.48. I'm writing this one. I'm writing this one, this part. Multiplied by 50 millimeter, which means that divided by 1,000 to be meter. So it's 604 kilonewton. So that was 1,000. This is 600. They are comparable, right? So that this is positive 600. It goes to the left-hand side will be 1,000 minus 600 for something equal to something delta 1y, right? Oh, sorry. Yeah, delta is negative. Yeah, delta is minus 50 because it's negative in the opposite of x direction. Yeah, that's true. Thanks. So you should put minus 50, and it goes to the left-hand side and will be added to the 1,000. It not always, but sometimes, in most cases, these things make sense, physical sense. For example, in this case, 1,000 kilonewton is pushing point number 1 to the left-hand side. So if somebody grabs it and brings it down, it's easier to push it. That's why 1,000 is added to 600. But if you had the settlement upside, I mean upward, it would vice versa. It was resisting whatever you're doing to push the point number 1 to the left-hand side. If you had the settlement upward, the result was 1,000 minus 604. Means that they are not along together. They are compensating each other. So this is the effect of settlement, and all in one, you will calculate the unknown deformation delta 1y, which is the only unknown deformation for your example. Right? You have, 5 of them, 4 are 0. One of them is minus 50 millimeter, and one is unknown, which is now known. When you have delta 1y, the rest of the, actually in this point you can say my structure is analyzed. That's it. I have done the analysis of the structure. My structure is analyzed. I know all the deformations. When you know all the deformation, your structure is analyzed. The rest are some other outputs you need, which are internal forces or support reactions or internal stresses. All of the other byproducts can be calculated based on the known deformations, right? So, for example, here you know that this is something we calculated. This is minus 50 millimeter. These are 0. You have this equation. So if you get the benefit of, we got the benefit of this equation, the second one, to calculate d1y. But if you get the benefit of the other equations like 1, 3, 4, 5, 6, you can calculate the support reactions. Like, for example, this is just calculating the delta 1y. But for example, for the first equation, f1x is this line multiplied by this vector, which means you have everything in the right-hand side, don't you? So in the right-hand side, you have a 6 by 6 matrix, everything clear. And the vector of deformation is totally clear because you know all the elements in the vector of deformations because it's solved. So f1x, f2x, f2y, f3x, f3y, you can calculate all of them and you can get all of the support reactions. And I don't have the rest of potential interest here, but you can continue the example by calculating the internal forces as well and checking your calculations by writing down the equilibrium equations at node number 1, for example, to see if all the forces are 0 in the x direction and in the y direction. All right? Any question before we proceed to the next one? So we can have 10 minutes break and then continue with this example, which the main difference is having a spring. That is something that can be combined with any sort of structure, like truss structure or frame structures later on. It's very important to understand what the spring does. So can we have 10 minutes break and we be back on 11 o'clock, okay? So, shall we continue? When you have a spring in your example, whatever example it is, a spring means like a bar element. This spring, this spring with K as a constant is exactly like a bar element which has A E over L equal to K. Exactly. And the deformation of a spring is only along the length of the element, not vertical, perpendicular to the length of the element, right? This spring only can move vertically at both ends and not move horizontally because of the spring. Node number 1 can move horizontally because of the other elements, all right? But the internal force in the spring is either compression or tension. It means axial force, right? So when you have a spring, if I didn't have a spring, I had 3 nodes, 1, 2, 3. Each node has 2 degrees of freedoms, altogether 6 degrees of freedoms, right? It means that, for example, delta 1 x, if I call, for example, this is x, this is y, for instance, delta 1 y, delta 2 x, delta 2 y, delta 3 x, delta 3 y, right? We had 6 degrees of freedom. However, I know delta 1y is the same delta at one of the spring's ends, right? When you have a spring, your spring has connected to node number 1 here, okay? But you have other end of your spring, which you need to name it node number 4. So having a spring means that you will have another node added to your problem, like node number 4. All right? So you have 4 nodes instead of 3 nodes. And node number 4, without having any support, can generally have delta 4x and delta 4y. But I know that delta 4y will work with my spring, and delta 4x doesn't do anything, right? So generally, I can have 3 nodes, number 1, 2, 3, and node number 4 because I have a spring, right? So it doesn't mean that we have 8 degrees of freedoms. To be honest, we have 7 degrees of freedoms because I have 6 degrees of freedoms because of node number 1, 2, 3, and 1 additional degree of freedom because of node number 4 in y direction. But we'll see how we will deal with these 7 degrees of freedoms. But if you like, you can call it 8 degrees of freedoms. That's fine. But delta 4x will not enter to your mathematical formulation at all. You will see that. Principally, you have 7 degrees of freedoms. If you didn't have the spring, you had 6 degrees of freedoms. And for elements 1 and 2, the procedure is exactly identical with what I've ever done with the previous examples, right? Just write whatever we've done for the previous example, like element number 1 connects node number 1 to 2. So calculate C and S, assemble that 4 by 4 matrix, and wait for the other elements to be fed into the big matrix, okay? So if I want to know, we will do that in 1 second. But if I assemble those kind of matrices, all right, for element number 1, element number 2, and element number 3, which is the spring, later on, I should say the big matrix for the structure is, assume that I don't know it's 7 by 7 or 8 by 8. What degrees of freedoms do I have to write at the top for my hints? Let's start. We have delta 1x, delta 1y, delta 2x, delta 2y, delta 3x, delta 3y, and delta 4y. Seven. That's why I'm saying it's 7 by 7. I don't write delta 4x there because delta 4x will not contribute to your problem. You will see this in the next slide. All right. Let's start with element number 1, 2, and then 3. All right. To see how we can calculate the individual stiffness matrix. Tell me when I reach to the same point that you had the issue. For element number 1, I just put it here to remember the numbers. Okay. For element number 1, we can say it's connecting node number 1 to node number 2. You can say node number 2 to node number 1. That's fine. And we know this is x, this is y. We define it. We can define some other coordination system. That's fine. So, for example, here, for element number 1, C, here, C is xj minus xi, means x2 minus x1 divided by the length of element. What is the length of element? 5 Newton, isn't it? Right? S is y2 minus yi. Y2 is yj, end of element. This is I, this is j. I is beginning of the element, j is end of the element. 1 connects to 2. 1 is I, j is 2. That's why I'm saying y2 minus yi, y1 divided by 5. 5 is the length of the element, right? So you can say x2 you need to calculate this distance. What is this distance? If it's x, we have a triangle like this. If it's x, that's 45 degrees. This is x as well. This is 5. So it means that 2x 25, x2 is 12, or 25 divided by 2. X is, I can say 5 divided by root square of 2. Or, yeah, that's fine. So, why do I need that? Because of x. So, x2 is 10 minus 5 divided by root square of 2. Minus x1 is 10 divided by 5. Right? 10 minus 5 divided by square root of 2 is this distance. See, this distance is 10 minus 5 divided by square root of 2. Is it clear or not? Not? Yes? Yes. For sure. On Wednesday, when some of you were practicing the E-tabs, I was calculated this as 3 meter point something. So the question is that, what is this distance and this distance? I know this is 10 meter and this is 5 meter. Okay? We have a triangle here. This is 5 meter. This is 45 degrees. All right? Don't look at me like you don't know what is 45 degrees. If this is 45 degrees, this is thank you, 45 degrees. This is 90 degrees. Good. For a triangle, 245, 190 degrees, this is equal to this one. Right? Because you can write the definition of sine or cosine for this 45 will give you, for example, if you write cosine of 45 is, let's call it A and call it B. Cosine of this 45 is A divided by 5. Cosine of this 45 is B divided by 5. So the left-hand side is cosine of 45. The right-hand side, A over 5, B over 5. So A should be equal to B. Right? And for any sort of triangle which you have 90 degree as one of the angles like this, you can say A squared plus B squared is 5 squared. Don't look at me like you don't know where does it come from. If you don't, it's okay. Just ask. So we know that A is equal to B. So it's A2 plus A2 is 5 squared. Or 2A2 is 5 squared. Or A2 is 25 divided by 2. Or A is square root of 25 divided by 2. This 25 can get out of here. It will be 5 divided by square root of 2. Or 5 divided by, like 5 square root of 2 divided by 2. Is it okay? So I just calculated this distance, which is 5 divided by square root of 2. What is this remaining distance? When the whole distance is 10 meter, this part is 5 divided by something. The remaining, this part is 10 meter minus 5 divided by square root of 2. Is it clear? Good. So if you put your X and Y here, like X, let me change the color. if you say my x is this one, this is y, when I ask you x for point number 2, this is the x for point number 2. This is the x2, right? This is the x1. X3 is what? X3. X3 on the x-axis for node number 3. Yes, 0. X-axis, remember, every axis is like a ruler. I just put the 0 of my ruler at the origin of the coordination system. My 0, my ruler 0 is here. So x3 is 0, isn't it? Let's practice for y. Y is another ruler here. The 0 of your ruler is at the origin of your coordination system. What is y3? 0. What is y1? 0. What is y2? That's correct. This distance, which is equal to this distance, is 5 divided by square root of 2. Right? So you know how to say x1, x2, x3, y1, y2, y3. And that's all you need to calculate CNS for all the points. Is that clear? Good. Shall we proceed to the next slide? Okay. Here we are. We want to say for element number 1, it's connecting node number 1 to node number 2. That's why I'm saying C is equal to, see, this is I, this is J. C is xj minus xi divided by Lij. Means x, you tell me. X, louder, everybody together. X2, don't be shy, scream. Minus x1 divided by 5 meter. X2. What is x2? Absolutely correct. 10 minus 5 divided by, 5 square root of 2. Minus x1, 10 divided by 5 meter. This goes away. I have 5 divided by this one. Eventually you will get minus 1 divided by square root of 2, which is obviously equal to this one as well, which is this you see here. Okay? Let's do the same for S. S is yj minus yi divided by Lij. I'm talking about element number 1, connecting node number 1 to node number 2. It is y2 minus y1 divided by L. It is y2 . Who said 0? Who said 0? Were you? Y2 is not 0, please. All right? Minus y1, 0. You're right, but this time. L, what is L? 5 meters. It will be 1 over square root of 2, which is obviously equal to this one, which is this here. Right? So this is C, this is S. When you have C and S, you only need to calculate E A over L and multiply it by this 4 by 4 matrix, which you have the formula C2 CS minus CS, etc. Does it make sense? You should do the same for element number 2. So was your issue somewhere here in this slide? Which part? For this one, element number 1, calculate this one. What you get? But it seems that a factor of 2 have gone inside to make these 1 minus 1. Have you considered that? Let me calculate. Oh, no, this is not that one. This is, yeah, this is here. Okay. Let me clear out. This part, the question is how this will be this one. This part is equal to 1050 times 10 2 divided by 5. I just multiplied that one. Okay. It means that it's 21,000. Okay. This is 21,000 kilonewton divided by meter. All right. Which will be 21 times 10⁶ Newton per meter, which is 105 times 10⁵ Newton meter times 2. This 2 goes inside, and this is outside this one, right? It's the difference probably is this is here, it's kilonewton over meter, but this is Newton over meter. Probably that's the difference, wasn't it? You should always keep an eye on dimensions. No, I just see, I just multiplied everything here. Okay, this is still kilonewton over meter. This is still kilonewton over meter. I multiplied this one by 1,000 here to transform kilonewton to Newton here. And I just said, okay, 2 times 105 is 210, isn't it? And 10⁵ will be here. So this 2 goes inside. The remaining is this one, which is exactly this one, but in terms of Newton over meter, right? So, is it clear for everyone? You should repeat it for element number 2. The same procedure. Nothing, no trick, no point, no hint, nothing. You should repeat it for element number 2 by saying like it's connecting node number 1 to node number 3, and just follow the procedure. You will come up with K2. I have K1 and K2 for elements number 1 and number 2. And I know that for element number 1, which connects number 1 to number 2, it means that this is delta 1x, delta 1y, delta 2x, delta 2y, right? Just as a hint for myself when I want to bring them to the big matrix. For element number 2, which connects number 1 to number 3, this is delta 1x, delta 1y, delta 3x, delta 3y. All right? Just keep them for later on. But for element number 3, for element number 3, you can follow the same procedure as the bar elements, or you can simply say the element number 3, this one, has a stiffness matrix 2 by 2, which is K 1 minus 1 minus 1 1, and the degrees of freedoms are delta 1 y for element number 3. You should say which one is connecting to what. Number 4 connects to 1. Okay, it means that the x direction, the local x direction for this element is like this, and this is delta 4x, and this is delta 1y, right? So the first one is delta 4x, delta 1y, delta 4x, delta 1y, right? This is the K for element number 3, right? Exactly like you had it before. The 2 by 2 element matrix, which connects 4 to 1. So I'm just using the same terminology as the coordination system for other elements. It's connecting 4 to 1. So it's delta 4x, delta 1y, the first end and the second end. So I just, when I assemble the big matrix, okay, when I assemble the big matrix, I should put these 4 elements into the right places, right? So for the big matrix, it's not here, but for the big matrix, you should have a sort of 8 by 8, but the 8 row and column will be 0, but 7 by 7 is enough, like delta 1 x, delta 1y, delta 2x, delta 2y, delta 3x, delta 3y, out of space. The big matrix is delta 1x, delta 1y, delta 2x, delta 2y, delta 3x, delta 3y, and delta 4y. 1, 2, 3, 4, 5, 6, 7. And the same here. Delta 1x, delta 1y, delta 2x, delta 2y, delta 3x, delta 3y, and delta 4y. And I know that I have a 4 by 4 matrix for element number 1. You can put it in the right places. For number 2, in the right places. And for the spring, which is element number 3, you have K1 minus 1 minus 1, 1. This is delta 4y, delta 1y, right? Delta 4y, delta 1y. So this one with the k, I mean, this one goes to here. This one goes here. Delta 4y, delta 4y. Yeah. This one, let's name them, whatever they are. Or we know what is they are. This is k. K goes here, right? This minus k goes delta 1y, delta 4y. It goes here, minus k. Delta 4y, delta 1y. This minus k goes here. And this one goes delta 4y, delta 4y, delta 1y, delta 4y, delta 1y, delta 4y, delta 1y, delta 1y, k here, right? So the spring has 4 elements. They're going here. However, we will have 2 different matrices for element number 1 and 2. They will need to be fed into this matrix. And which rows and columns should be eliminated later on based on the supports, restraints. For example, we have 7 rows and columns. But this number 2, rows number 2, rows corresponding to these 2 should be eliminated, right? 2x and 2y, and the corresponding rows. We have support at node 3. These should be eliminated, right? We have number 1 free, right? And we have number 4 restrained, right? So this should be restrained as well. So from the 7 by 7, only rows number 1 and 2 will be remaining. Means only 4 elements here will be remaining. And only this k will get into the calculations for determining the unknown deformations. The other k's are somewhere else. So this k will be added to the other values coming from the elements number 1 and 2, will be combined with them and will get into the process of calculating the unknown deformations. Right? Does it make sense? The spring contributes to the solution by adding a k into the problem. So it's now your job to continue the way to get the solution. You know the solution. You have the ETABS to validate it. The solution, the correct solutions are these. But when you get home, try to assemble the big matrix, try to find eliminate the other rows and columns, grab the right part of the remaining matrix, inverse it. This is the remaining matrix. Inverse it and see, you will get delta 1x and 1y here. These are exactly those in the ETABS you had on Wednesday. And if you have delta 1x and delta 1y, you can calculate internal stresses in different elements. The formula, you have it. We did it for example number 3.5, if you remember. It's easy to just, you need to follow the formula and you have all the deformations. Or if you need to calculate the support reactions, I don't know if I have the support reactions. No, I don't have. So you can calculate the support reactions and control check your calculations if you have done correctly or not. All right? Questions? What's one? You're multiplying exactly these numbers or your numbers are different? You mean this one? This is the formula. Okay. So this is E. This is L. For element number one, okay, C and S, C is negative, S is this one, okay? So you can say it's like -1. I'm saying just this part. 1. If you put square root of 2 over 2 here, it will be -1, 1, 0, 0, 0, 0, -1, 1, right? So this is 1 by 2 matrix. This is 2 by 4 matrix. If you multiply them, you should come up with some sort of 1 by 4 vector, right? So the vector will be equal to square root of 2 over 2 multiplied by 1. I'm trying to multiply this by this is 1. This by this is -1. The third one is -1 and 1. Okay? So this number is 0.707. So this part is exactly this one. Okay? This part is delta 1, and this part is delta 1 to 4. It's number 1 connects node number 1 to 2. This is delta 1, this is delta 2. These two zeros are delta 2. These two are delta 1. All right? So what doesn't work here for you? Is okay? Okay. So it's always this part is the first delta, the second delta. Element number 1 connects node number 1 to node number 2. So this is delta 1, this is delta 2. This comes from the multiplication of this one, and this is E over L. If you multiply this 1 by 4, this is 4 by 1. Let me clear up a little bit. This vector is 1 by 4. This is 4 by 1. The result of multiplication of these two should be 1 by 1, a scalar. It's not a matrix, it's not a vector. So this is a scalar. The final is a number, which is this one. Right? The same for sigma 2. You should do the calculations to be able to solve a problem in the exam. It's not like just if you take a look and it seems okay, that's fine. No, it's not fine. When you get home, you should get a pencil or a pen and a piece of paper and practice it. Put the example in front of you without answer, okay? Just try to solve it and compare it to the results, to the correct result. And do all the mathematical solutions by yourself. Just a pencil and a calculator, nothing more. And that brings you skills, necessary skills to solve finite element problems. When you look at them, okay, everything looks fine. That's beautiful. I know that's beautiful. But when you grab your pencil, write it down, you will say, oh, what was that? Why this number is negative? Why this is positive? Why I cannot multiply these? Why? A couple of why will be arise. So you need to deal with every individual errors, problems. Some of them will be easily solved. Some of them you need to ask me, email me, ask me, we will discuss. And that brings you some sort of skills to solve a problem. Does it make sense? This week, again, I'm reminding everyone, if you haven't had the chance today, please do so. Go to the IT lab, follow those 3 videos for these examples, 3.5, 3.6, 3.7. And please, 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 for the week ahead or tomorrow, whatever, take a piece of paper and a pen or pencil and absolutely solve these 3 questions, 3.5, 3.6, 3.7. They are extremely important to build up a skill in your mind, how to deal with a truss structure. And if you will be able to solve these 3 problems independently on a piece of paper, I assure you, you should be, you will be, you certainly will be successful during the final exam to solve the truss structure element. As well as it will build a sort of skills in your mind to better understand the next session that will talk about beams, and the other one will talk about frames, because they are some sort of elements which will have everything we have today, plus some extra degrees of freedoms, which are rotation, right? So we are going stepwise ahead to more complex problems, and it's very vital for you to stay in each step, deeply understand what is the concept for the truss, what is the difference to the beam elements, to the bar elements, and what is ahead for the beam elements and frame structures. So take the time and stay on these 3 examples. If any part of the example is not clear enough, crystal clear, don't wait until next week. Just drop me an email, ask your questions, and I will reply to you as soon as I can. Otherwise, if you couldn't, just ask me next week. All right? So please, please, please do this. Otherwise, you will get lost easily during the future sessions. Good luck, and this is for today. Class is dismissed. See you next week.